Okay, ready? All right, let's get started. Okay, so today we're going to do dimensionality reduction. Uh, this probably gets old, the usual, like, what have we done already? Linear stuff. Maybe I'll just go to the most recent weeks. More recently, for example, we did the Chernoff bound, starting with random graphs and giant component. It turns out that like going from small to big component was a Chernoff bound in disguise. You just have to look at it the right way. Uh, then we did randomized rounding. So that was sort of going from these continuous random variables, interpreting them as probabilities and starting to pull out discrete solutions. Yeah, here's where I wish I could erase stuff. Last time we did distinct elements and F2 estimation, moment estimation. Am I off by one? Yeah, there's a slide missing for online algorithms, and we also did online algorithms before that. So today, I guess this will really be lecture 9. We're going to do dimensionality reduction, and we're going to get some practice with Gaussian random variables, which maybe you've seen before, but we haven't played with in this class. Okay, so all right, you've all seen the phrase before. When I was like in your shoes, this was like the hottest phrase before deep learning. We had big data. It was very exciting. Okay, so what's so big about big data? Maybe there's like two aspects. One is you just have many pieces of data, right? So, okay, they're talking about like internet scale things, downloading the whole internet, one piece of data for every website or something, right? Just large, many pieces of data, individual pieces. But the other aspect is kind of how big uh, each piece is, okay? And in particular, representing things numerically as high dimensional vectors. So, okay, so here's maybe some applications. Um, okay, someone give me a sentence, any sentence. You can say any sentence, just give me a sentence. This happens every single time. Like you think you're clever, but every year someone says, someone give you a sentence. Okay, so some sentence like someday I'll get a class with some personality. Yeah, well, oh well. Randomized algorithms 2026. Here we come. All right. So someone give me a sentence, and so the idea is to encode this as a vector. So you're going to make a vector where every entry corresponds to a different word. So maybe someone is this coordinate. I guess it should maybe be alphabetical, so maybe it's somewhere in the middle. Someone, maybe I should put at the end. A, me, give, sentence or something. So they all are like different parts of this vector. So this is like a massive array. Okay. So okay, I have this occurs once, this occurs once, something like this. Okay. So it'd be like a 1, 0 vector. Everything that's not marked is like these are all the words that don't occur. Okay, so the array is mostly 0. Okay, and it's just marking which words in a bitmap are in it, or I guess it would be numerical. A word can occur twice. Uh, what would be like the dimensionality of this vector? How wide should it be? Loosely speaking. Yeah, it'd be like the size of a dictionary or something, right? Number of words in an English dictionary, plus typo, plus whatever, emojis. Okay. All right, so that's one way to kind of represent documents, just record how many times each word occurs numerically. Okay, nothing deep there. But they might take you could take the same concept, right? And to get a slightly richer representation, sometimes in data mining or NLP, instead of doing bag of words, they'll do bag of phrases. Okay, so for every phrase with 3 words, that'll become an entry in the table, in the array. Okay, so now what's the dimensionality of this kind of vector if I filled it out for bag of phrases? Yeah, it might be like a number of English words to the third power or something. Okay. So so I guess the only point of this example is it's not hard to think of how you can even take something that's already high dimension and do some intuitive things that gets even higher dimension. Okay. Here's maybe a couple other examples um, of large networks. Any graph can be represented as an adjacency matrix, right? So let's start with like the World Wide Web. Uh, it's an n by n matrix. What is n roughly? Or in English? I don't know the actual count. So it'd be like number of websites, right? And then you just have like some 1-0 matrix keeping track of who links to who. Websites will be asymmetric. Okay. Social networks can also have an adjacency matrix. What would it be? The dimensions of social networks? Yeah, number of users, number of bots, right? We'll tell you the dimensions of the social network or something, right? Okay. But the point is that these numbers get bigger and bigger. Okay, no big deal. Okay, now if you're actually running uh, using these vectors for some reason, you know, maybe we don't really need uh, the actual explicit representation. Okay, if you're actually doing like clustering things or you're doing regression, if you had the vector, you have everything you need, but kind of more directly, what might you need? Like, let's say you're just trying to do clustering. So you have a bunch of vectors and you want to put them into 5 groups and stuff based on similarity. What do you really need from those vectors? Sort of a vague question, yeah. Yeah, pairwise comparisons, if I was dealing with vectors and I was doing clustering, what would be a natural sense of pairwise thing? Oh, the L1 norm is certainly possible. Yeah. Uh, yeah, but in general, the distance between two vectors, right? At some level, I don't really need actual x and y if I have access to the distance, right? Um, in other cases, another notion of similarity, I might only really need to be able to compute the dot products between things to basically be able to run something that looks like gradient descent to do some regression, right? Maybe I want the length of certain things. That's very similar, of course, to distance, okay? And at some level, right? So my goal is to take these massive vectors that are full of information but too big to do anything, very swiftly with. I want to try to compress them, or I want to somehow decrease the size. But maybe we just want to try to preserve some of these properties. Okay, if I can maybe try to preserve the dot product between vectors in their compressed form, if I could preserve the inner product, that's the same thing, the length or the distances in between, if I have some kind of data structure that kind of forgot all the original vectors, but could still tell me the distance between any two vectors, that might be enough to run some basic clustering algorithm or something, right? Okay, so that's the high level idea. So dimensionality reduction, right? The issue is you have tons of dimensions. And so here's what we're going to show today. We're going to show that kind of morally, log n dimensions is enough if you have n vectors. Okay, you have n vectors in effectively infinite dimensions. And I'm saying that log n dimensions is basically enough. So let me break that down a little more. We are going to come up with some kind of map that's going to take your very, very high dimensional vector, and it's going to somehow assign each vector to one with modest, moderate dimension, log n. Okay. And more specifically, if you want to say preserve all the distances up to a 1 plus or minus epsilon factor, so you're off by 10% or something, you need about log n over epsilon squared dimensions. Okay. So this is very nice because it's independent. It has nothing to do with the dimension of the domain. It's completely independent. It does depend on the number of different vectors you're trying to deal with, but that's mostly so you can take a union bound over all the vectors. Okay, but the real thing is it's independent of the domain. Okay, so it's a very nice, uh, exciting idea. Uh, Especially if they haven't seen it before. Does anyone want to guess how? Like crazy ideas. It might be. It should sound too good to be true. Yeah. Okay. So distances can only be so far away from each other. So let's see. I mean, you have to, oh, can you say it again? Oh, okay. Yeah. Uh-huh. Oh, oh, well, okay, so to set up all bit strings. Oh, no, I think this will really be a quantitative thing where you just want to say, uh, just in case there's any confusion, before in that dictionary example, the dimensionality is where all the bit strings are, and then we just have ones and zeros encoding whether those bit strings occur. Uh, but yeah, this is not mapping generic. This is just a particular. We're just trying to preserve vectors, and other objects would require different considerations. Yeah. Okay, so there's an idea. Um, okay, so you have some very high dimensional space with tons of basis. That's my attempt to draw lots of basis vectors. Okay, and you're going down to smaller number of basis vectors. And then, what if I, randomly assign each basis vector to a different basis vector or something? That's at least a randomized map. Okay. Now, this needs to preserve. So this is not what we'll do, but can we see with this is but it's an interesting idea. Can we see why? So does that make sense? So you're going from a thousand dimensional space into like a 10-dimensional space. So you just figure out like the thousand basis some set of thousand basis fixed set of thousand basis coordinates in the first space, and then 10 basis coordinates in the second one. Okay. And then for each of the ones on the input, the first coordinate, second coordinate, third coordinate, I'll assign a random coordinate in the output, first coordinate, second, third, and I'll just kind of sum up basically. Okay. Uh, um, okay. Now the claim is that we need to preserve all pairs of distances uh, with high probability for any given input set of vectors. So someone come up with a input set that'll challenge this example? Yeah. Yeah. So if our input was the basis vectors themselves, they're all like roughly square root 2 from each other or something, right? Because they're all kind of like this. And you're mapping a bunch of things that are supposed to be moderately far apart into a small set of vectors. So you're going to get some collisions. A bunch of those pairs are going to be right on top of each other and have distance 0. Okay. So that idea won't quite work. Just by pigeonhole, you're going to get a lot of vectors that are far apart that are going to be collapsed onto each other. Whereas our goal is to preserve all of the pairs. Mm. All right, so that alone is already kind of bizarre, right? Because you can take many, uh, yeah. Okay. Um, Good. Okay. So yeah, so that's already kind of interesting, right? Because you're able to take many basis vectors and actually that are far apart and then keep them far apart in a smaller space. Yeah. All right, anyone? Yeah, okay, the punchline's coming, and then I won't be able to take it back. So, all right. So, yeah, maybe I'll just explain the thing here. What we're going to do is we're going to make a linear function. Okay, it's going to be a linear function. So that means it's going to have some form like f of x is equal to ax. Okay, there's going to be some scaling, which in our case will be 1 over square root k or something, where k is the target dimension. Don't worry too much about that. What's more interesting is what is a going to be? Okay, so a should be very wide because the input dimension is very large, and the output dimension is, looking like log n or something. I shouldn't have chosen red. Now everything's red. Okay, so it's a very wide matrix. It's wider than I've drawn here. Okay, the question is, what are the entries? Does anyone want to guess? Yeah, they're going to be random numbers. What's your favorite random numbers? And that's not random if it's 7 every time. Yeah, we are going to do a matrix full of Gaussians. Okay, so there's the complicated looking version, but every single entry of A is going to be a random Gaussian. We'll talk a little bit about what that is in a moment. You've seen it before, probably. Okay, but it's just a symmetric, simple random variable. So every entry is going to be independent Gaussian. Okay, so A is completely oblivious. It doesn't look at your input at all, which is kind of nice, right? This is not studying your input and coming up with something clever. It's a completely oblivious embedding. It's like very symmetric. It's putting some mysterious random Gaussian variable every entry, and it scales things down just to make the expectations kind of work. Okay, we'll do those calculations in a moment. And that magical matrix with high probability is going to preserve the distance or the length of any input vector. Okay, so in fact, what we'll directly show, so f of x is just applying this matrix. What we're really going to show is that you preserve the length of any single vector with high probability. Okay, if you choose the output dimension to be like log n over epsilon squared. So that's what we'll show. As a consequence, you're going to get all distances between all pairs. Okay, in this statement, they look at one, but actually one follows the other. Do we see why? Okay, so this is saying, look, if I take any 2 points and I map them and I measure their Euclidean distance in the smaller space, it's going to match up to some small approximation Euclidean distance in the input space. Okay, f is a linear function. So why does the second follow from the first? Okay, so because f is so simple, it's just applying a, that this is equal to f of x minus y. Okay, and there's only, n squared pairs we have to worry about. So we'll preserve all of the x minus y pairs, just because we're preserving any particular vector with probability 1 over n to the 10 or something. Okay, so just by getting one pair, guarantee for one vector, and then using the very nice fact that our embedding, they're called embeddings, is linear, we're able to get all pairs of vectors, their distances. Okay, we're just applying f to all the differences. There's not that many differences. And you'll show in the homework that with slightly different guarantees, you'll also be preserving things like dot products. F of x, fy is going to be pretty close to xy. You're going to get an additive guarantee, as you'll find out in the homework. Okay, for dot product, it's a little bit different. Okay, and it turns out that as long as you're kind of preserving dot products and lengths and things like this, if you open up like your favorite linear regression algorithm, right? You're trying to do linear regression with, all these kind of observations, these rows, right? That's like, oh, there's so much data, I can't fit that in my computer. So you compress the rows first. You only have like log n over epsilon squared features or something, which are kind of the output of this thing. And then you run your favorite regression on the compressed vectors. Okay. you're going to be able to reason and kind of relate the output back to something in the original space. As long as sort of, because in data analysis, when you open up, you're just playing with things like dot products and lengths and stuff like this. Okay, so you'll preserve the key structural kind of linear algebraic properties. Okay, you'll lose a 1 plus epsilon, but if you're in some space where the data was so big, there's nothing else you could do, you're happy with that trade-off. Yeah.
Is the inner product only going to be approximately equal, or is it like equal for high probability?
Yeah, so with high probability. So all of these directly will be with high probability for any particular vector, any particular pairs of vectors. And the way we set it up here is like, oh, let's say you started with a set of n vectors, you want to embed all of them. So we'll be able to take a union bound over all these things. So in the end, you'll get all of your fixed set of inputs, or in general, it's an oblivious embedding that for any particular input works as high probability. The latter will imply the first was a union bound. Okay. All right, any questions here? Because it's sort of a bizarre tool or idea if you haven't seen it before. At least it was for me when I was in your shoes. Okay, great. So actually, the punchline of this is not just that A is like the world's silliest matrix. It's that if you're very comfortable with Gaussian random variables, this is like the most obvious statement in the world. Okay, in fact, so this was done by Johnson and Lindenstrauss, and they're both fantastic mathematicians. But Lindenstrauss reached some age where they put together some collected works of his best papers, in his career. Right, he's a functional analysis guy, and this paper, of course, has an infinite number of citations, right? Because every single data mining machine learning paper is going to use this trick. Yeah, infinite number of citations. But this paper will not make it into his selected best works because it was too easy, I think, for Lindenstrauss. Okay, but I'll try to convince you of what I mean. Okay, so that's the goal, is basically if we get a very high level of comfort with Gaussian random variables, then we'll see why this kind of naturally follows. Okay, so obviously this is really a prop to do some Gaussian stuff. Okay, so let's do some of that. Any questions though about the statement? All right. Okay. So all right, Gaussian random variables. Uh they are some distribution. They're parameterized by the mean, the average, and the variance. Okay, they like to write sigma squared for the variance. Okay. And anyone, you've probably seen it before. Anyone know the definition of a Gaussian random variable? Yeah. Yeah. Oh, I should maybe. So Gaussian is another name for normal. Yeah. So what is the normal distribution or Gaussian random variable? Yeah, it'll look like a bell curve. So you've seen it before. Does anyone remember the official definition? Yeah. Whatever. Just
For square root of 2 pi sigma squared times e to the power of x minus u squared over sigma squared.
does that sound familiar? Okay. All right. Lots of. All right. So the definition is the nicest, most pleasant, convenient random variable ever. Okay. This is where all your dreams will come true. If you are of a certain personality. Okay. It's the world's nicest random variable. Okay. For example, suppose I have something with a normal with a fixed mean and a fixed variance, and suppose I add a constant alpha. Okay, you will get another Gaussian, but the parameters change. How do the parameters change? If I add a constant, yeah, the mean shift. You just slide things over. Okay, maybe that's not so surprising. Okay, what if I scale things? I multiply it by 5. Variance by 25. The variance will go up by alpha squared. The standard variation will go up by alpha. Okay, we'll do these calculations later. Okay, this is what you're hoping for. Should the mean change as well? Yeah, shouldn't it? It should, right? Okay. All right. Let's just awkwardly move on. Okay. All right. If I give you two Gaussian random variables, different means, different variances, and I add them together, I'm going to get another Gaussian random variable. So this is very nice. Right? If I take two 0, 1 random variables, add them together, I don't get a 0, 1 random variable. If I take two Gaussian random variables together, add them together, I get another Gaussian random variable. But what's the mean? What's the variance? Hopefully it's correct. Yeah, you're trying to tackle the hard one first, right? Yeah, so that's like the variance. Let's see what it is. Oh, the variance just adds up the variances. The standard deviation will do that. Funny, will be the square root of this, and that's where it gets messier looking. And then the mean will just get added together. Okay, so again, you don't really have to know anything about it. It's just whatever you want it to be. You got it. Okay. All right, here's sort of an exotic one. Uh, I won't try to motivate this. We'll see why this is useful in the moment. Okay, so suppose I have a Gaussian random variable between 0 and 1, and this is called the a certain moment. All right. Actually, for what it's worth, for those keeping score at home, x squared when x is Gaussian is sometimes called a chi-squared distribution or something, but I neither know how to spell it nor anything else. Okay, that's just a name. But so this is called the moment. I'll explain in a moment why this is such an important quantity to look at. Okay, and well, there's no way you know the answer to this, right? But it's saying, okay, I have some value between 1/2 or something, less than 1/2. You know, the interesting case is when it's a very negative number or something. Uh, and I exponentiate it. Now you have to be careful about exponentials, right? Because Gaussians do have a tail, and you might be worried about what happens when I exponentiate the tail, right? Goes out to infinity. So the real question is like whether this is going to be a relatively small value or relatively, unbounded value. Okay. The answer apparently is 1 over square root of 1 minus 2t. So actually gets fairly small when t is even like negative. Okay, good. All right, so good. Okay, so in addition to having one Gaussian random variable, I can have vectors where every entry is a Gaussian random variable. Okay, so we sometimes call these like Gaussian vectors. So these are vectors shooting off into space where one coordinate is one Gaussian, the other coordinate is another Gaussian. They're sampled independently. Okay, so a Gaussian vector. So I wrote n to the k, meaning there's k coordinates, each of which are coming independently from the same distribution with the same mean, the same variance. Okay. Okay. Um, okay. So what is the expected length of such a vector? It might help to expand out. Uh, Also, this is the first class where we're kind of doing vector notation, linear algebra notation, stuff like that. So just pause me if you haven't seen it before. And then hopefully, like the first lecture will be awkward, but then as we get a little bit more practice, we'll do it from time to time. We'll get a little bit more used to this notation. Okay. All right. So here I'm looking at the Euclidean norm. So that's just the sum of squares. Okay, and high dimensions, but it's just like 2 dimensions. And I want to know the expected value of basically the sum of squares. Sorry? Yeah, okay. Well, let me make this easier. I think I did a bad job. Suppose I told you the mean was 0 for all of these. Now what's the expected length?
0.
Okay, so expected length, so I think what you guys have in mind then is that if I looked at the expected sum of xi's, then I would get 0. But if I'm looking at as a vector the Euclidean length squared, I'm really looking at the sum of xi squared. So what would be the expectation? Yeah, sorry? K sigma squared. So each of those terms, it's the expected value of xi squared. That's the variance. The mean is 0. I should have had mean 0 all along. Okay. So the expected value is the variance is mapped to the lengths as a vector. Okay, the reason we want to start getting into vector language is because each row of that matrix was a Gaussian vector. Yeah. Mm-hmm. Okay. Yeah. Okay. Good. All right. Now here's where things get a little bit more sophisticated. Okay. This is talking about how concentrated the length is to its expectation. Okay. So you have random Gaussian vectors. So every entry is a random Gaussian, and you're looking at its length, which is some kind of sum of squares. Okay. And the question is that length all over the place, or is it well behaved? Okay. And so this lemma is going to say that it's pretty well behaved. Okay. So for example, it might help to plug in some values here. Okay. So if for alpha I put in like 1/2 here, 1/2 and 1 minus 1/2. Okay. If at least I chose a reasonably good value, I hope that I did. This will be some quantity less than 1. Okay. 1/2 times square root of e, I think will give you something less than 1. Okay. And so this is saying that you have some value less than 1, and it's dropping off exponentially in k. Okay. So what's that saying? The higher the dimension, okay, the more concentrated the length of the random vector. Yeah.
Is like the n to the k the 0 sigma squared. Does that just mean that n dimensional? Oh, k dimensional.
Yeah. So this is the number of dimensions. So I have k entries. Each of them are Gaussian, mean 0, variance sigma squared. Okay. And this is saying, okay, the odds of being, I don't know, let's say 1/2 of the length is plummeting exponentially in dimension. Okay. And likewise here, the odds of being twice, okay, 2 times the expectation is also plummeting in k. Okay, so it's concentrated, for lack of a better word, exponentially in k. Okay, so high dimensional Gaussian vectors, as far as their length goes, are extremely predictable. Yeah.
So that one bound with the epsilon squared minus the mean.
Okay, so let's we'll come back to prove this then. So here would be a version for that 1 minus epsilon, 1 plus epsilon. Okay, and there's white space to do this, but basically we're going to use the previous one and plug in the right values.
Is that worse than the one that we showed just now?
Is this one worse than just a minute ago?
Yeah.
I think this is basically comes from plugging in. 1 minus epsilon for alpha and 1 plus epsilon for alpha. And then maybe I got lazy about fighting for constants. I might have done some simplification. Okay, but it's essentially the same bound. Just saying, what if alpha is 1 plus epsilon, alpha is 1 minus epsilon, because that's the regime we're kind of interested in. The previous bound was just kind of more general. Yeah, we can even do it. We have the technology. So, okay, so here's the old bound here. Can you see? It's probably is that readable? Kind of readable? Okay. All right, so let's just plug in then. So if I plug in 1 minus epsilon into here, we're looking at like 1 minus epsilon e to the 1 minus epsilon. Oh no, got wrong. It's 1 minus alpha, so e to the epsilon k over 2. Okay. Now this is where things get tricky for us because I have sort of suggested in the past that 1 plus x is basically e to the x for small x. But of course, if they were equal, you just get 1 to the k over 2. That wouldn't help us, right? So now we have to actually be a little bit more detailed. Okay. Hmm.
Wait, what did we just plug in? What did we get?
So this is we haven't proven this yet, but this is sort of the more general one for any alpha less than equal to 1. And now I'm going to plug in 1 minus epsilon into alpha. So right. So here, here's alpha is 1 minus epsilon, and then 1 minus alpha becomes epsilon. Okay. Good. Let me just make sure I do it correctly. I don't think I need to cheat. Okay. So what do we need? Okay, so if you look at something like e to the minus epsilon, okay? So this, is 1 minus epsilon plus epsilon squared over 2 minus epsilon cubed over 6 plus epsilon 4 to the whatever 4 factorial and all that, right? Now, when we take epsilon very, very small, okay, these terms, epsilon cube, epsilon 4 is epsilon to the 5th, they're all going to be completely dominated by epsilon squared over 2. Okay. So this is going to be greater than equal to, say, 1 minus epsilon plus 3 epsilon squared over 4 or something like this. Okay. If I did this, if I set this up a little bit different. So if I instead did something like e to negative epsilon, you're right. Let's do 1/4.
Does it have to be greater than 1 half?
Does it have to be great? Oh yeah, I just want it to be greater than 1/2. I just wanted to choose the conservative value for small epsilon. For sufficiently small epsilon.
Wait, why are they about less?
Oh, we want that to be greater.
Okay, let me just one sec. I'm confusing myself. This one's actually simpler. Okay. All right, let me do this better. Okay, so for sufficiently small epsilon, this epsilon to the 4th term is going to get killed off by the epsilon to the 3 term. Okay, and if I had kept going, your epsilon to the 5 term, which would have been a minus, would have been killed off by the epsilon to the. Oh no, I got it backwards. Uh, yeah, okay. Let's do this carefully. Okay, if I'm doing greater than equal, then that would be okay. Yeah, okay, we're on the same page. Okay, so if I compare it to like e to the negative epsilon minus epsilon squared over 2, okay, then you would start getting stuff like 1 minus epsilon squared over 2, plus, epsilon plus epsilon squared over 2 squared over 2 minus plus, I'll do minus and I'll just keep writing plus. Epsilon plus epsilon over 2 cubed over 3 factorial plus and so forth. Okay. And what I can start doing is I can use this epsilon squared over 2 term to annihilate the epsilon squared over 2 term that arises from here. Okay. So what I want to start arguing, if I had done this a little bit more slowly, is the whole thing will come out to at least 1 minus epsilon. Okay, for sufficiently small epsilon. Okay, so to put everything together, we already knew that 1 minus epsilon is less than equal to e to the minus epsilon. That's always been true. But there is a slightly smaller gap. 1 minus epsilon is less than equal to e to the negative epsilon minus epsilon squared over 2, or maybe the 2 needs to be a bigger constant. But there's some wiggle room. There's a quadratic you can squeeze in there as well. Okay, if you expand it out, do it slowly. So what that goes into here is that this thing becomes at most e to the minus epsilon, minus epsilon squared over 2 or something, maybe 4 to be safe, since that would match the claim, times e to the epsilon k over 2. Okay. And now what you'll get is that this term will cancel out with that term. And then you're left with epsilon squared over 4 times k over 2. That gets you the k over 8. Okay. So that epsilon squared is just squeezing in as like the slight analytical gap between 1 minus x and e to the x for small x, e to the minus x. Okay, just like very carefully looking at the function for small values of x. Okay, so what we're really saying is that this term, e to the negative epsilon squared, maybe divided by 8, is representing this barely sublinear term. Okay, we know that 1 minus epsilon is very close to e to the epsilon. In fact, 1 minus epsilon is slightly smaller than e to the epsilon, bounded by this roughly e to the negative epsilon squared term. Okay, so it is a very close to 1 kind of thing, right? E to the negative epsilon squared for very small values of epsilon. What matters, though, is that you're exponentiating and you have the k, right? We can choose k to be at least 1 over epsilon squared to get rid of the epsilon squared, right? And now you're winning. Now you're really going downhill. Okay, so all that really matters is we get that term to be slightly less than 1. The epsilon squared isn't great, of course, but we get that term slightly less than 1 so that the k does the rest. Make sense? Okay. If we did the other bound, which is there's space for, we would end up doing the exact same thing. Okay. All right. So the interesting part then is establishing this thing, alpha e to the 1 minus epsilon to the k over 2. Okay. All right. So, okay, I just want to make sure I don't mess this up. All right. So we never really did the proof of the Chernoff bound. If we had, the first few steps would look really familiar. So, okay, so we start from here. Okay. And at some level, what we want to do, well, basically the only thing we know how to use is Markov's inequality, but okay, so what we're going to do is we're going to kind of ramp things up exponentially. So I'm going to exponentiate both sides. Let me just leave the sign blank for a moment, and then I'll let you guys fill that in. E to the negative t alpha, the expected length. Okay. And the question is, what goes here? So I'm raising both to the e to the minus t. Yeah, so this will be greater than or equal. just to make sure we're on the same page. Okay. Good. All right. So I've kind of exponentially, so I've started something, we haven't lost anything. This will be exact, right? Because e to the minus t, it's going to flip the ordering, but otherwise completely preserve ordering, right? A is bigger than b if and only if e to the minus a is smaller than e to the minus b. The probabilities are still the exact same. But at some level, the exponentials are going to heighten things, right? Because that's what exponentials do. Okay. Does anyone want to guess the next step? There's not much we can do, and it turns out you know what we can do, or you know the tool we're going to use. The most famous inequality. We have several in this class, but what would be one such? Bernoulli's inequality?
What the heck is that?
I'm sure there is one. Yeah. Okay, we're going to use Markov's inequality. Okay, so that's going to yeah. Oh, okay, one sec. So one thing I guess nice is this is k, so I'm just going to write k from now on. Okay. So normally Markov's inequality would be the expected value. Sorry.
The dimension is also
Yeah. Okay. Let me make things simple. We're going to assume the variance is 1 because the claim is scale invariant. So if I assume the variance is 1, nothing changes. Everything is scalar. In which case our expected length is k, so I don't have to write this e of x squared all over the place. Okay. So normally Markov's inequality is going to give us something like the expected value of this thing divided by that thing, right? So e to the negative t length squared times e to the t alpha k. Okay, because it should be e to the negative t alpha k in the denominator. So the negative on the negative t cancels out with being in the denominator. Okay. Okay. Good. Oh, we do. Okay. Okay. Good. Fine. Now what? So now we got to deal with this term. So okay, let's try to use this. The one thing to be careful about that inequality, which we do want to use, is that this is for a single Gaussian random variable. So we want to get there. And this is for, we're currently dealing with the whole kind of Euclidean length. So I want to go from that whole vector to single Gaussians. How do I get there?
So then it's almost the expected values.
Okay. So let's take this slowly. This is e to the negative t, the sum over all I, xi squared. Yeah. And then e to the whatever. Okay. And so you really have like e to the x1 times e to the x2. I mean, e to the x1 plus x2 plus x3 is e to the x1 times e to the x2 times e to the x3. And each of those e to the xi's are independent. Okay. That's the key step. That's also the key step in the Chernoff bound. Okay. All right. So now what? Just figure out how to deal with one of these terms. Yeah.
So we plug in one over.
All right. Perfect. So now we'll use the thing that was mentioned before. So you're going to get like 1 over square root 1. Okay, but we're applying it to negative t, where t is something bigger than 0. So you'll get 1 plus 2t raised to the k power. Okay. Or it might be a little bit more convenient to remove the square root and write raised to the k over 2. So the over 2 is doing the square root for us. Okay. Times e to the t alpha k. Okay. This is where things get more annoying. So now you just want to choose the best possible value of t to make this as small as possible. Okay, so we don't have to do it slowly. I mean, in two completely, but at some level you can write this as e to the t alpha k minus k over 2 log of 1 plus 2t. Okay, where I've just like taken the thing and put it in the corner by taking logs. Okay, and now if I want to minimize e to the x, I just need to minimize x, right? Because e to the x is monotonic. And since I've already done the calculations for you, don't delete that. You'll want to choose alpha is over 1 plus 2t. If you solve it, it'll give you alpha as 1 over 1 plus 2t, which is the same as saying t is equal to 1 minus alpha over 2 alpha. Okay. If you plugged everything back in, okay, which I don't think you want to watch me do, you're going to get that this is at most alpha e to the 1 minus alpha k over 2. Okay. All right. So what are maybe the key steps? At some level, there's some level at the end where it's like, okay, here's the thing. Let me take some calculus, see what comes out. Okay. So really the key steps first is kind of exponentiating. Okay. Somehow that's going to be very powerful, right? Because at some level, like we're worried about cutting off tails. An exponent is going to really highlight the tails for us. And then we apply Markov's inequality to the exponentiated form, and then we break things up independently, and then we get all these individual moments. Okay. Here it became helpful to understand that the Gaussian had a very nice moment, and everything else followed. Okay. Yes. Oh, sorry. Did you have a question? No, no. Adrian had a question.
Could you explain how we went to like from the probability of expectation? Just like how we applied Markov's?
It should be less than.
Again. Okay. So Markov says, the probability of being twice the average is at most 1/2. So here's sort of the average. And if the denominator here was twice the average, you'd get 1/2. So Markov's inequality in the numerator will have the expectation at the left, and it'll just have the value on the right in the denominator. All we need is that things are non-negative. In this case, because we're exponentiating, it's automatically non-negative. That was where we applied Markov's inequality. Yeah.
Did the product we're using the fact that the xi's are like IID. So
They're independent in particular. They don't have to be distributed the same to take them apart. It doesn't matter if they're independent. Yeah. Okay, good. So the other concentration bound, what are the odds that it's much bigger than the length? Exact same style calculation. It's just that since you're already in greater or equal, you'll do e to the t instead of e to the minus t. Okay, but the exact same morals will apply, which I'm assuming you'll be even less enthusiastic to see that than you were for the first one. Okay, so maybe we'll take that as given. Let's try to figure out. Maybe the fun part is figuring out how to apply this. Okay, so what do you know? You know that things like sums of Gaussians are Gaussians. You know that Gaussian vectors have well concentrated, at some level. Okay, there are some messy calculations. You also are aware of some complicated looking density function. But qualitatively, the right-hand side represents a lot of stuff we understand about Gaussian random variables. Just scrolling down, we know how to sum them together. We know how to scale them. We know how to look at a Gaussian random variable and figure out its average length. It's going to be the sum of variances, which will be, say, k times 1 if they're normal Gaussians. And we also know that a Gaussian random vector, at least for high enough dimensions, is almost always the exact same length, whatever its mean is. Okay, so yeah, the calculations look messy, but you actually know a lot qualitatively about Gaussian random variables and their sums and their vectors. Okay, and we should be able to play on that intuition to try to prove this. Okay, so let me yeah. So maybe here is the more direct form we'll try to prove. For any particular vector, hopefully you can see this. Okay. For any particular vector, if I pass it through that same function as before, with high probability, with e to the minus k type of failure probability of error, I think there should probably be an epsilon squared here. Okay. It'll preserve the length of x. Okay. Well, all I'm saying is let's just focus on figuring out why we preserve one vector. The rest will follow from union bounds and things like this. Okay. So let's fix x. Your input vector x. If you want to make it easy, since everything's linear, you can assume that's a unit vector. Okay. So you just want to show that you're going to output, once you scale down, roughly a unit vector. So let me put like some squiggly lines here. With high probability, you're going to get a unit vector, right? So that's morally the idea. Okay. And I'm claiming we can do this without so many messy calculations. But now the question is why? So A, remember, A is going to be a big vector. Every entry is a Gaussian random variable. Yeah. X, right? You're going to apply it to X. And you can think of X as sort of like a vector, something like this, right? X1, X2. X1 is going to get applied to everything in the first column. X2 is going to get applied to everything in the fourth column. We don't even care what dimension it's coming from. Okay. So X4 is going to get multiplied in everything in that column. And then they're all going to get added up. Okay. Yeah. So what we can ask ourselves, for example, maybe for starters, what does one row of this look like? Like, let's say I'll call this row, this vector A1, right? So A1 is every entry is a Gaussian, right? So it looks like something like this. Okay. So in that case, AX1 or whatever, that'll be the inner product of our Gaussian random vector and our input x. What does this look like?
Summation of the components from A1 I x I equals 1 to the dimension.
Okay, so yeah, okay, if we're just going to write out what the inner product is what you mean, this is what it literally means, right? But what is this? Yeah, it's a sum of Gaussians. So in particular, it is. It's another Gaussian, right? So this thing is distributed from a Gaussian distribution. What does it mean and what is the variance? Maybe we can go more slowly. One of these entries, what is this? This is a Gaussian. What's the mean? And what's the variance? Xi squared. Okay. So now if I look at the whole sum, that's the sum of these Gaussians. What's the mean? Zero. What's the variance? Sorry. What's the variance of our sum here? It'll be the sum of xi squared, so it'll be the length of x squared. Okay. Okay, so now what does that look like, right? We have this random, yeah, so okay, so now you have all these like, you also have a2x, right? That's the output from the second row. That's going to have the same distribution, right? You're doing like k of these for some k, akx, right? And these are all the individual entries of your output, right? That's the first coordinate, that's the second coordinate, that's the last coordinate. Okay, so what does that say about ax? What is ax? It's a vector, yes, in particular. Okay, so ax, you know, if you want to write kind of compactly, right? Looks like this. It's a random Gaussian vector. Every coordinate has variance norm of x squared. Okay. And what do we know? What do we know about these vectors?
Expected value for the
Okay, so what's the expected value of ax squared? What's his expected Euclidean length squared?
k x squared.
Yeah, it's just going to sum them up. Okay, that was not one of the harder calculations from before. Okay, and what else do we know about the length of ax? It's a random vector, right? What do we know about the length of ax? It's going to be super concentrated, right? Was the probability error plummeting exponentially in k? Right? So the probability of ax squared being at least 1 plus epsilon times the expected value, okay, is going to be like e to the negative epsilon squared k over 8, okay, where 8 is hopefully a correct number, but who cares, okay, okay. So basically ax is just a random Gaussian vector, and you already know everything there is to know about a Gaussian random vector. Okay, if you're trying to get 1 plus error, as soon as you start making k bigger than 1 epsilon squared, oh, okay, it's practically guaranteed. Yeah.
Since AX is a vector, like it's a multivariate normal distribution, should the second argument be like x squared times I? Because it's a variance covariance matrix.
Okay. So you're worried about. Okay. So maybe another thing to point out. Important thing to point out here. Okay, so the question is like, is there some covariance matrix or something? Each of these random vectors are also independent. So everything's independent. So it really is being distributed from a random Gaussian. So even though it's all based on the same x, every coordinate is still completely independently distributed from mean zero, variance, length of x squared. So all this is doing is just applying what we know about the length of ax squared. Recognize that ax squared is actually just a random Gaussian vector, Euclidean length squared. So I think there's no consideration of multivariate stuff that needs to come into play at all. So yeah, so maybe it's a little confusing because A, you start thinking of a square, you're thinking of a m by n kind of thing, but AX represents a vector, a random vector, and that's really what we're analyzing. A random vector with independent coordinates. Okay. So that's all this claim is doing. It's really just saying that AX is distributed from this distribution, and everything about its length is just a fact of high dimensional random Gaussian vectors. Okay. Now, doing all the calculations to get to this point is kind of messy. The good news is you only have to do it once in your life. They're all facts, right? I mean, it might seem more complicated because I'm being clumsy. But imagine if you did this for a living and you're used to Gaussian random variables, then this is not a surprising application. If you're comfortable with number random variables, then you say, oh yeah, I can do this useful thing. That stats class finally paid off, right? Okay. All right, so that's really the punchline. Good. So that, you set k to be log n over epsilon squared. Now you get 1 over poly n probability error. And now when we go back to our original application of trying to embed, n different points and all their pairwise distances, you can take the union bound of error, you won't mess up any of the points or any of the differences between them. Okay. Again, this is just really an expression of the fact that high dimensional Gaussian random vectors, their length is completely concentrated. And the conclusion should be totally counterintuitive, right? For example, it deals with this bad example of like mapping a bunch of basis vectors into a smaller space. Yeah.
So a smaller space, why can't you just put it into an even smaller?
Oh yeah, why can't you put it into an even smaller? So one thing also amazing about this is that it had nothing to do with even the dimension of the input space. So it's really more running into the in fact, first of all, uh, 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 I mean, you just want, every time you do this, you lose a little bit error. So first of all, you're trying to, there's no point in going into like so the question is, can you go just into a smaller space after that? If you're doing these kinds of calculations, there's no point in not just going directly to the smallest space you're going for. Otherwise, at least if you break up the analysis at 2, you're kind of incurring 2 1 plus epsilon type of errors. But I think basically, you're choosing your dimension k just based on what are the probabilities you want for a single particular vector. So in the story I gave you, you wanted to embed all the points, right? But if you just wanted to guarantee that, like, oh, I have a bunch of input points, I just want to make sure most of the points are good and maybe some will get screwed up, then you could have chosen k to be a smaller number. You don't have to go all the way to log n if you don't need to get everyone correct or something. Okay, so there's different trade-offs. Yeah.
So you mentioned taking the union bound. Do we know how many points there are?
So in this original statement, the original application is, okay, suppose you have n points and you wanted to preserve all of their geometry, basically. Then you need like log n over epsilon squared. Yeah. Yeah. Well, that's also true. I mean, yes, A1, A2 is another linear map. Although it'll be kind of messy to like look at all the random variables, right? Because they're all going to be correlated with each other and stuff.
This fund is tight, so basically you cannot, if you want to specific about them.
Okay, yeah, that's another good point is that this is also basically tight. Yeah, whether there's an exercise or not, I don't remember. Yeah. Okay, at some level, you still need to spread out, a bunch of equal distant points from each other from the input. Okay. All right. Good. Good. Okay. So in the time we don't have, I'll talk about what we could have done. in another life. Okay, just because maybe you should at least be aware of some of these things. Okay, so it is true that there is a density function for the Gaussian random variable. Okay, so this is the probability of x taking a particular value given a particular mean and sigma. Of course, a density function is never the actual value, but you can integrate it over certain intervals. At some level, I think this density function is reverse engineered to be nice. If you're taking a real analysis class, then you might have done these exercises, like you integrate and you see this all adds up to 1. If you do xfx for the expected value, you'll get the mean, and this will get the variance. Somewhere in here, you need to do this really cool thing. Well, you want to do your polar coordinate trick. So you actually look at this you want to look at this thing squared to actually, or this thing squared, and then you do polar coordinates. It's the only way I know how to do it. So I left some blank space so that you can do it, for fun. This will follow pretty straightforward fashion. Okay, so one thing kind of cool that maybe I want to highlight: how do you show that the sum of two Gaussian random variables is Gaussian? You could mess around with the density functions and be in a world of hurt. Here's maybe a different slick approach. Okay, so the first thing to point out is that if I look at a Gaussian ensemble, so I just get a bunch of Gaussian random variables, sigma squared, okay? And if you look at the densities and you kind of multiply them together, okay? All of the e to, I think here I'm just assuming the variance is 1 to keep things simple. All to the e to the negative x squares kind of add up to each other, okay? And the point is that the density of a vector is something just a function of the length, right? This is just x squared. Okay, so that's the probability of it taking on a particular vector. In particular, it's rotationally invariant. Doesn't matter what direction it is, it only matters the length will dictate the probability of taking on that particular value. So when you move on to the next thing is that an orthonormal matrix just represents a rotation. Okay, so if you take a random Gaussian vector and you rotate it, you get another random Gaussian vector with the same distribution, because the distribution only depended on the length. Okay, now part 3 says that if I take a random Gaussian vector and I take any vector u and I look at the inner product, I'll get a Gaussian random vector. So this is sort of a fancy way to just say sum of Gaussians is a Gaussian. Okay, but I'm claiming it follows from rotational invariance. Why? For simplicity, you should assume that u is a normal vector because it's the scale invariant anyway. Yeah. Say it again.
Caused by the addition of the random Gaussian variables will not affect the actual.
Yeah. So how am I going to somehow encode my one vector into a rotation? Okay. So you can make a matrix U, a bigger matrix U. Maybe U's a bad choice. I'll put a line underneath, where the first row is the given vector, and you just extend it to an orthonormal basis. Okay. So then the little ux is the first row of ux1, which is following a normal distribution, because ux is just a rotated normal distribution, or high dimensional. Okay. So rotational invariance actually gets you for free by encoding it, your sum as the first row of a rotation, that the sum of Gaussians is a Gaussian. Okay, that's the one trick I wanted to show off. So that comes for free. I guess this is sort of important, but we don't have time for it. But it's only maybe read the notes to check in on how to analyze the individual moments of the chi-square distribution. Okay. Okay. Thank you.